Okay, so we will talk now about one new thing, or one other type of materials, or molecules. So we talked about the acids, we talked about the bases, we talked about water, and now we'll talk about the salts. And for the salts, we are more interested in the salts that satisfy the law of mass action. So in case of highly soluble salts in water, this is not gonna be our concern in this chapter, because we are interested in the salts that are sparingly soluble in water, or have low solubility in water. Why? Because these are the salts that the law of mass action can be applied to. So if we have a salt, it's gonna be composed of an acidic radical and a basic radical, so it's gonna take the shape MA. Again, M is the basic radical, A is the acidic radical, and for the MA, this is gonna be dissolved in water, and as I mentioned, they are sparingly soluble. They have low solubility in water, so part of them will be soluble in water to convert into M plus and A minus. This is the aqueous part, which means that they are dissolved in water, and this is not dissolved in water. And you can see this a lot. You can put a salt, even for the soluble salts. If you put a lot of table salt in water and you stir it very, very well, you can find some of the salt that cannot dissolve in water anymore, because it has already been saturated with the salt. And this is the same here, but in this case we have the solubility going in forward and backward direction. Again, we can apply the law of mass action, and then we can put the K of the salt, which we call the solubility product. So K now, just to remember what we mentioned before, we have K, which is the K for acid, which is the acid dissociation constant. We talked about the K for B, which is the base dissociation constant. We talked about K of water, which is the ionic solubility or ionic product of water. And now we will have Ks, which is the solubility product of a salt. Okay, so the Ks is gonna be the concentration of M plus multiplied by the concentration of A minus, and again, this is insoluble in water, so it's not gonna be part of the equation. Again, as we always say, that the K is constant. Okay, and it's usually measured at 25, as we did in water. And we here have in this table some values for the sparingly soluble salts in water. And you see here, like barium sulfate, it is 10 to the minus 10, calcium carbonate 10 to the minus 9. So we have even 10 to the minus 28. So the values are very, very, very small for these sparingly soluble salts in water. So if we have a salt like this, then we will have, as we did before, we will have X moles and X moles for each one of them that is dissolved in water. Or we can call it the concentration. So the X is the number of moles divided by the volume. So the K for salt is gonna be the multiplication of these two, which is X squared. Okay, so the X is the concentration of each ion in water. So this is what we're gonna get. This is right in case of, for instance, if we talk about AgCl, or it's gonna give Ag plus Cl minus, so the K, the solubility product, is gonna be the X squared. And if I know for AgCl, it's 1.1 multiplied by 10 to the minus 10, then X is gonna be square root of Ks, which is gonna be around 10 to the minus 5. Okay, so this is one thing that we can get, is to know how much or what's the concentration that we will get when we dissolve this salt in water by adding or by using the solubility product. Let's see another case, for instance, for PbCl2, which is lead chloride. This is gonna be different because it's gonna give Pb 2 plus 2Cl minus. And now when we write the equation for the solubility product of the lead sulfate, it's gonna be the concentration of Pb ions multiplied by the concentration of Cl ion to the power of 2, because I have this 2. Okay, or you can say that this plus Cl minus, so this multiplied by Cl multiplied by Cl, so it's gonna be the same. So in this case, I can tell also from the stoichiometry of the equation that this is gonna be x, and this is gonna be 2x, because each 1 mole of this or x mole of this will dissociate to give x of this and 2x of this. So when I substitute, it's gonna be x multiplied by 2x to the power of 2, which is gonna be 4x to the power of 3. So it's not always the x and x, it depends on the concentration, and you will always notice that this and the power are the same. The coefficient of x and the power is always the same. So this is how we can calculate the concentrations or the dissociation in case of something like lead chloride. Let's see another case, for instance, like bismuth sulfide. This is gonna break into 2Bi 3 plus 3s2 minus. So in this case, what we will get is that we have 2x and we have 3x, and the k is gonna be the 2x to the power of 2 multiply 3x to the power of 3, which is gonna be 4 multiplied by 27x power 5, and it's gonna be 108x power 5. Okay, so this is something that is it's kind of nice that you can know exactly what is the final concentrations from only the solubility product. There is one other thing that is important from this solubility product of the salts, which is what we call the common ion effect. To understand what we mean by the common ion effect, let's say that or let's consider the salt as a person who has 2 legs. So it's a person who has 2 legs. Okay, and as he goes, he has to put his 2 feet on the ground so that he can move forward. And let's say he is walking over a river, and there are specific locations that he can walk on. So he needs to walk. So he first walks on the first part, and then to move here, so he will put his 2 legs on the second part, and so on. But at one point he will find only 1 slot, so he can put only 1 leg, and in this case he cannot take this step. And he cannot take this step because the other part here is not present, or it is blocked. There is something that is there, so he cannot put his leg in here. And this is exactly what happens to the salt. For instance, I have the example of silver chloride. So if I want to dissolve the silver chloride in water, I have to make sure that there is a space for silver and space for chloride to dissolve in water. If I have a space for silver but not space for chloride, it's not gonna dissolve. Or I can have very low solubility because I don't have any available slots for silver to or chloride to dissolve. This is called the common ion effect. This happens when, for instance, I have a salt like silver, sodium chloride. It's a highly soluble salt in water. It's already available in water, and this salt is dissolved in water with any concentration, let's say 0.1 molar. This is the concentration of silver sodium chloride in water, which means that the concentration of sodium ions equals the concentration of chlorine ion equals 0.1. Okay, so I have already chlorine ions, which is the common ion. It's an ion that's present in silver chloride and it's present in sodium chloride. So this is a common ion in the two salts. If now I want to dissolve the silver chloride in the solution that already contains sodium chloride ions, I know I mentioned this before in the previous or in a few minutes ago that for where was it? Yeah, for silver chloride. That for silver chloride, I was able to calculate the K by using the solubility product, and I multiplied the concentration of chlorine by the concentration of silver, assuming that they both are the same. But in this case, I have a value that's different for the concentration of chlorine ions. And in this case, what will happen is that I will say that the Ks for the silver chloride is going to be the concentration of silver multiply the concentration of chlorine ions. Now I have the chlorine is 0.1. I have this value not from silver chloride but from sodium chloride. And now I have the value of K, it's constant, it's not gonna be different. It is 1.1 multiplied 10 to the minus 10, and by substitution I would find that the maximum solubility of silver is gonna be 1.1 multiplied by 10 to the minus 9. This is the final concentration, which is compared to the concentration of 10 to the minus 5 that I achieved before without having the sodium chloride in the solution. So this, the common ion effect reduces the maximum solubility of the sparingly soluble salts in water because of the presence of the common ion, the ion that is common in the two cases for the chlorine in silver chloride and chlorine in sodium chloride. And you'd see that the reduction in the concentration is huge. I have 4 orders of magnitude. It's 10 to the minus 5, and here it's 10 to the minus 9. So I have 4 orders of magnitude reduction in the concentration of the salt in water just because of the presence of the other ion. And again, the solubility or the common ion effect, it's the solubility of a salt in a solution is reduced in presence of a common ion in the solution. So this is all for this video. So I'll see you later. Goodbye.